The plan was to discuss a couple of things more and then go over the chiral, just the class of the pionic chiral Lagrangian with sources and use the other notation just so you can see the mapping from the notation we've been using to what's in some of these 2-loop and 3-loop chiral perturbation theory calculations so that you can read the papers more easily. So what I want to discuss is the baryon masses in chiral PT. And it's a paper from Elizabeth Jenkins from, all this stuff is ancient, Nuclear Physics B, 368, 1992, 190. The part I'm doing now basically was done by Murray Gell-Mann in the 1960s. This paper is about doing the one-loop corrections and so on. But there's some features about the Lagrangian which I wanted to point out. So, okay, so the part which has been erased, we were working in the pure chiral limit. And now we have, as for mesons, the extra m that we have, a mass matrix, and we are working to first order in the mass breaking. And our Xi, as usual, goes to LCH dagger is HCR dagger. So if I now take C dagger, M C dagger, that transforms like H, C dagger, M C dagger, H. So the basic rule is that you just put X's or Xi daggers on either side to convert everything to be transforming under H. And you can do that because one of these two forms kills either the R or the L. So, okay, and I'm going to do this in SU3. So the mass is a 3×3 matrix. The baryons are 3×3 matrices. And the mass Lagrangian is P sub D times the trace of B bar V, C dagger M, C dagger plus the Hermitian conjugate, C M dagger C. B sub V, okay, sorry, I should put, what did I do here? This is wrong. This is B sub D. So this is a D term, and this is the anti-commutator with B sub V. And then there's an F term, which is the same thing, except that you replace this with a commutator. So just like for the axial current, because there are two invariants between three octets. And now there's another term, which is the so-called sigma term, which is the trace of M sigma dagger plus sigma dagger M. So this is the same as the mass term we had in the meson sector, but multiplied by an extra B bar V, B sub V. So this is like the one baryon version of the baryon mass term. So for pure pions, this term doesn't contribute because there's no baryons, but in the baryon sector, you get a contribution. And so what Gell-Mann did was basically not have any of the X's. You're just using pure SU3 to calculate the masses. When you put in the X's, you get the corrections to the baryon to pion interactions, essentially, or the baryon pion interactions proportional to the pion fields. And the sigma term is a 2 baryon, 2 pion interaction, which is kind of, as far as the group theory is concerned, as far as the flavor theory is concerned, it's not coupling the baryons to the mesons. Okay, it's like independent. So let's work in the limit where, I mean, just to save time, and you can work out the general case, 0, 0 ms. So I'll forget about isospin breaking. I only put in the mass of the strange quark. And then what you get, okay, so now the proton and neutron are degenerate, the 3 sigmas are degenerate, etc., because of isospin. And M nucleon is M baryon minus 2 BD minus BF times MS minus 2 sigma MS. M lambda is m baryon minus 8/3. So again, these are things, I think I put these on the problem just to do the traces and just verify you get these. M sigma is m baryon minus 2 sigma ms. M c is m baryon minus 2 bd plus bf ms minus 2 sigma ms. So first of all, if you're just looking at the masses, you can see that everything has this combination mb minus 2 sigma ms. So you can't separate these two terms from each other. This is like some overall mass for the baryons, but the sigma term gives you some ms-dependent contribution. So if you could tune the strange quark mass, the average mass of this multiplet would vary with sigma times the strange quark mass. So now with lattices you could do that, but okay, previously you could not. However, the MB term doesn't come with any pion couplings connected with it, but the sigma does. So by measuring pi nucleon scattering, you can determine what's called the sigma term, and then there's like a whole controversy in the literature as to what exactly the value of the sigma term is. I think Anant mentioned this as to whether it's 56 MeV or 70 MeV or whatever. So this is what you get. And you can see, okay, from the group theory that, okay, you're getting some numbers times the decouplings and numbers times the F couplings, and that's what I meant on this part which was erased. When you do the axial vector decays or the axial vector currents, you will get some numbers times Ds and some numbers times Fs, and these numbers are determined simply by taking this trace and just reading off the coefficients. No, it's the baryon masses are not connected with the chiral symmetry breaking condensate. This is not a chiral symmetry breaking mass. It's just some overall, there's some confinement in the baryon. So in the limit that the quark masses are 0, the baryons are still massive. They're not Goldstone bosons. Yeah. So at this level, okay, sigma, this, you can just absorb the sigma into here, but then you have BDMS and BFMS and MB minus 2 sigma, 3 parameters and 4 masses, so you get the famous Gelmano-Kubo relation. So this is the baryon version of the Gelmano-Kubo formula, which says that the average of the nucleon plus the Xi mass is 3m lambda plus m sigma over 4. And one thing to note is on the right-hand side, it's not the average of the lambda and sigma masses because there are 3 sigma states and 1 lambda state. The 3 is in front of the lambda, not in front of the sigma. And experimentally, this is like 128 MeV versus 135 MeV, which is pretty good for just a relation to first order in SU3 breaking. And you can go to higher orders, and Elizabeth, by combining this with the 1/n expansion, was able to get certain combinations of masses involving the baryons and the decouplet baryons, which work to fractions of an MeV, and was actually able to apply this to the heavy baryons with B mesons in them, and got predictions before the states were measured to better than 5 MeV, which was much better. The lattice results disagreed with the data at like 25 MeV, so it was much better than that, and it's just coming from this group theory type relations. Okay, the other application you can make is to heavy meson chiral perturbation theory. So the B and the B star, the D and the D star, and like baryons, they're going along, let's say the B or the B star, interacting with pions, and even though they're heavy because of the heavy quark, and you can still consider, say in the rest frame of the B or the B star, some soft pions interacting with them. And the BB star mass difference is about 50 MeV, so you can have soft pions, and they can make transitions between the B and the B star, and so on. And from the point of heavy quark effective theory, there's some heavy quark, and there's Q bar, but you shouldn't literally think of Q bar as an anti-quark. That would be taking the quark model too literally. But what this is called is the light degrees of freedom. Matthias called this the light degrees of freedom, or the Brown muck, which is a technical term meaning light degrees of freedom, which has the quantum numbers of Q bar. And there are two states, the B and the B star. The B has spin 0. The B star has spin 1. And if you take a heavy quark and a light quark, where the light degrees of freedom are spin 1/2, and the heavy quark is spin 1/2, you can combine them to form a spin 0 or a spin 1 state, which are the B and the B star. And if you flip the heavy quark spin, you can convert one into the other or whatever. So they form a single multiplet of heavy quark symmetry. And the way they're represented in heavy quark effective theory is you define what's called an H field with a velocity on it, which is 1 plus V slash over 2, which you should be used to by now. And B star mu, gamma mu, minus B gamma 5. So you're contracting the vector with a vector and the pseudoscalar with a pseudoscalar. So this is a 4x4 matrix in spinor space, which has both the B star and the B in it. The way heavy quark symmetry acts is it acts on the left-hand side. So the heavy quark spin operator would act by multiplication by the Pauli matrices on the left-hand side of HV. So you should think of the left, this is like a matrix with two indices. The left-hand side is like the heavy quark index, and so this is the Q index, and that's the Q bar index. So interactions with the light quark are sort of acting on the right of this. Interactions with the heavy quark are acting on the left. And actions of the spin operator turn the B and mix up the B and the B star. So that's the irreducible multiplet under the heavy quark spin symmetry, and the 1 plus V slash over 2 kills those other pieces. So you're projecting. So this is this thing, because otherwise you write it in terms of scalar, tensor, whatever, and those are all down when they're not there when you put in the 1 plus V slash over 2. And that's because you want a representation of the heavy quark spin symmetry, which is it's these two states which form that. So under heavy quark symmetry, H sub V goes to SQ H sub V. And under chiral SU3 cross SU3, this is, where is it gone? It looks like an antiquark. So under chiral SU3 cross SU3, HV goes to HV, H dagger. This is our famous H from the chiral Lagrangian. And that's because this object transforms like a 3 bar under flavor. It has the flavor quantum numbers of an antiquark. So now we want to write down the chiral Lagrangian for this object. And it should be familiar now. So you have H bar V, I V dot the covariant derivative, H sub V, the chiral covariant derivative acting on H sub V. So that's the kinetic term. And now the pions couple to the axial vector current, but it's the axial vector, and it's the axial vector coupled current of the light quarks. So the coupling here is G trace of H bar V, H sub V, gamma mu gamma 5, A mu. Okay, so remember that these are matrices, so I could put the gamma mu gamma 5 either between the two fields or on the right-hand side. So here it's acting on the light quark index. So if I make a heavy quark spin symmetry transformation, I get an S and an S dagger or whatever, the U, the corresponding exponential of this, and they cancel. You can have a term which is trace, let's call this G prime, trace H bar V, where the gamma mu gamma 5 is on this side, A mu, This violates the spin symmetry. And so this is down by 1 over mb, where b now is, or let's put it little b, the b meson, or the b quark mass, or the b meson mass, not b doesn't stand for baryon here. And that's because if remember gamma phi was like a spin matrix, and so the spin rotations don't commute with that. So at leading order in the 1 over heavy quark expansion, you can drop that. And so now you do the trace, plug this in, so that's another homework problem. And what this tells you is that there are two couplings you can have, B star pi, B star pi. And what heavy quark symmetry tells you is that they're both governed by the same coupling G. They're related to each other. And then you got to put in all the indices and work it out. And those indices are taken care of by the trace. Okay, why is there no BB pi couple? So this is not there, BB pi. It's not, it's absent. And if you do the trace, you won't find it. No, let's worry about phase space later. But I mean, the coupling can exist even if the physical decay is not allowed, because you can then do loops like this. Right, so you can do chiral loops, and you don't have to have a physical intermediate state. Yeah, so both B and pi are pseudoscalars, and you can't have a 3 pseudoscalar interaction. It violates parity. Now, this is a vector, and that's a pseudoscalar, and that's a pseudoscalar. Here you have 2 vectors and a pseudoscalar, and you can put in an epsilon symbol. There's enough indices to allow for that interaction. So I don't want to do the details of the calculation. So now you take this Lagrangian. This will have odd numbers of pions in it. This will have, from the V mu term, even numbers of pions in it. And then you can calculate stuff like this and SU3 breaking. And so some of the things people have done is like calculate the ratio of the SU3 breaking in the B sub S versus the B decay constants. So in leading order with SU3 symmetry, they're related, they're equal, the ratio is 1. But then you get some corrections which are of order mk squared log mk squared over mu squared, order p squared corrections from the one loop diagram, and so on. But these are so-called chiral logs. And they're calculable. So this is, again, this matter field formalism applies just as well to this. Once you write everything in terms of the H transformation, you can basically just write down any Lagrangian that you want. And there's a heavy quark symmetry here, so you can also look at D and D star. And the heavy quark flavor symmetry tells you that this coupling in the B system and the D system are the same, because you swap out the heavy quark, which was acting just like a Wilson line or something. The G doesn't change to leading order. So there's some 1 over m corrections to GB versus GD, but otherwise, to leading order, the G's are the same. So there's a whole bunch of phenomenology you can do, and, well, has been done with this. So this gives you the formalism. Wait, what do you mean? Okay. So yeah, so the question is whether the charm quark or the D meson system is heavy enough that you can do the 1 over n expansion and apply perturbative QCD at the scale. And the answer seems to be it's okay, that So for example, you can calculate the magnetic moment. I think Matthias wrote down the 1/m magnetic moment operator, and the coefficient of that in the B versus the C is governed by scaling between MB and MC, which is some alpha S at MC over alpha S at MB to the power. And it seems to be okay. Somehow the way the QCD works is that it sort of all of a sudden stops working. It's not like a smooth problem. Up 2 GeV is fine, maybe 1.5 GeV is fine, but you go to 1.1 GeV and it just, then nothing makes sense. So the charm quark is, you have to be a little careful, but it looks like this heavy quark effective theory seems to be doing fine for that. I mean, Matthias did these B to D form factors and all of this stuff, and the relations work. You couldn't apply it to the kaons, for example. That's complete disaster. So the S is not heavy. So yeah, so this was, I mentioned at the beginning, it's the charm quark may be a little not clear how heavy it is, and the S quark maybe is not light enough. So those are like the two questionable quarks. But you certainly can't treat the S with HQET, and you can't treat the charm using chiral perturbation theory. That's definitely out. Okay, other questions? Okay, so I thought what I would do in the remaining time, rather than try and do some new topic, was just explain the notation that people use. So you can look up some papers by Bainens, Colangelo, Ecker, which are the group which has done at least 2 loop, and I think Bainens has gone to some 3 loop calculations and so on. So if you can look at that papers and you understand what's going on. So the notation is little u, I mentioned this in passing, is e to the I pi over f. Capital U, which is little u squared, is e to the 2I pi over f. And the transformation for this is u goes to r u h dagger is h u L dagger, and capital U goes to r capital U L dagger. So I mentioned in passing that they put the left-handed transformation on the right and the right-handed transformation on the left, but okay. So in the notation I've been using, this is C dagger, and this is sigma dagger, because we have to swap where the left and the right. But because Mike C was e to the I pi over f, this also means that the pion flip sign. So between my convention, what I've been using, and this convention, you flip pi to minus pi, so that u is still e to the plus I pi over f, not e to the minus I pi over f. Okay, now let's look at what the QCD Lagrangian is. And now what I want to do is add what I call background fields or background sources. And we kind of did that with the mass term. We treated the mass term as what's called a spurion or some background field. Here I want to add in also gauge fields. So I have q bar left, ID slash plus L slash q left. So this is the QCD covariant derivative, and L slash is a background vector gauge field. So if you want, this is a source or a background field. Plus q bar right, ID slash plus R slash q right, minus q bar right, and I'll put a little m here, q left, minus q bar left, little m dagger, q right. And because of their swapping of lefts and rights, their little m is what I call big M dagger. You're sort of exchanging these two terms because you're exchanging lefts and rights. So this is a background scalar source. Those are background vector sources. And these are SU3 left gauge fields, and those are SU3 right gauge fields. If you wanted to, you could add a background U1 baryon number gauge field. But for the U1 axial, you cannot gauge it because it's an anomalous symmetry, and you can't gauge that. That wouldn't make any sense. So usually people don't worry about this. They're just gauging the SU3 cross SU3. And L mu would be L mu A TA, and its Hermitian. These are the SU3 generators. Similarly, R mu is R mu A TA. Sorry, L mu dagger is L mu, R mu dagger is R mu. Now, the reason this is useful is the weak interaction currents are living in this SU3 left entry, because you could have U bar gamma mu P left D, or U bar gamma mu P left S, with a VUD and a VUS, and these are both inside this 3x3 L entry, SU3 left. So we can calculate weak decays by picking out for the non-strangeness state changing decays this first entry, and for the strangeness violating decays this entry. Basically, okay, I don't remember which one. One of them is here. It's either here or there, one anyway, and the other one is down here. You know, the 1-2 entry, or the 2-1 entry, and the 3-1 entry. Maybe it should be 0-1-0, and then this one should be 0-0-1. These would be the generators corresponding to these transformations. And the other thing, which is sort of an accident, is that the electric charge operator, which is 2/3 on up quarks and -1/3 on down, and -1/3 on S, is a traceless matrix, and so it also lives in SU3. You don't need the U1 part. So we can also do electromagnetic couplings by picking out L mu as some photon times Q, and R mu is the photon also times Q, because the electromagnetism is a vector symmetry. And so I pick these matrices Q, and I guess with an E here for the charge. So I can do electromagnetic interactions as well. So these are like all special cases, or I can put both weak and electromagnetic in by putting these combinations of matrices in. Okay, is this clear? Now for the QCD Lagrangian, because of gauge invariance, you know that L mu has to transform like L mu L dagger, I think minus I d mu L dagger, and R mu has to transform like R mu R dagger minus I d mu R dagger. This is the L mu transforms like a gauge field under the SU3 left, R mu transforms like a gauge field under the SU3 right, and with this transformation law, we can make our SU3 left cross SU3 right symmetry, we can make it local now because we have gauge fields. So we have promoted our local global symmetry to a local symmetry with background gauge fields. And now a chiral Lagrangian will have these background gauge fields and has to be invariant under the local SU3 cross SU3 symmetry. Maybe I should say, so F left mu nu, the field strength tensor, is d mu L nu minus d mu L nu minus I L mu commutator L nu, and that transforms to L F left mu nu L dagger, and similarly for R. Okay, now I prefer this way, but the way this was originally written was in terms of vector and axial, so I can take this Lagrangian, delete the L, and put a P left here, and delete the R, and put a P right here. And similarly here, I can put a P left, delete the R, and delete the L, and put a P right there. And so the way the papers are actually written is to use Q bar ID slash Q plus Q bar V slash plus A slash gamma 5 Q minus Q bar S minus IP gamma 5 Q. So rather than use left and right-handed, the papers are written in terms of a vector source as an axial vector source and a scalar source and a pseudoscalar source. But you can just read off, plug in P left is 1 minus gamma 5 over 2. P right is 1 plus gamma 5 over 2. And you find that V mu is 1/2 R mu plus L mu. A mu is 1/2 R mu minus L mu. And the scalar source is 1/2 M plus M dagger. And the pseudoscalar source is I over 2 M dagger minus M. So you can go one way, and if you want to go the other way, maybe the best one is S plus IP is M, S minus IP is M dagger, and R mu is V mu plus A mu, and L mu is V mu minus A mu. So you can either go, you can go between the left-right version and the vector axial pseudoscalar or whatever version. Okay. Now, if you remember when we did the meson masses, we had a mu f squared, f squared over 4, the trace of d mu sigma dagger, and then we had b f squared over 2, the trace m sigma dagger plus m dagger sigma. So because of this relative 2 in the b, what people do is they define chi is by definition 2b times that quark mass matrix over there. You rescale it by 2b so that this term becomes f squared over 4, just like the kinetic energy term, and now you have chi m dagger, etc. Okay? It's just a historical convention. So, yeah, so it's this, which is 2b S plus IP, because that's what's M. So the chiral Lagrangian is written in terms of chi. You'll see when they write it. Yes, very good question. So let me add to this plus an axion field g squared over 32 pi squared g mu nu dual A. Now, if I make a chiral rotation, and I'm sure I will get the sign wrong, but if I make an e to the I don't know, alpha rotation here on the left-handed field, and e to the minus, so q left goes to e to the I alpha q left, q right goes to e to the minus I alpha q right, then theta goes to theta minus twice the number of flavors times alpha. So now pick alpha to be the axion. So this is theta. This is what I'm calling theta. So pick alpha to be the axion field divided by twice NF. Then this term's gone. The axion coupling is not there anymore. Instead, these mass matrices have a phase which is e to the minus I axion of x. So there's an FA here to make this dimensionless. The axion decay constant. So you get some FA. So M goes to M times this phase. Okay, but now we can just do chiral perturbation. So what you do is you do chiral perturbation theory. You can calculate the axion couplings. You can calculate the axion mass by just putting it in the chiral Lagrangian. And this is proportional to the unit generator. The pions are proportional to the traceless generators. But this is how you calculate the axion mass, axion couplings, and various other things. So yeah, so this is what you do. Yeah, so when now you have to do this fully. So when you do this transformation where this is an x, then so this happens in the mass, but you have to plug this into here, and you get derivatively coupled axions to the currents and so on. But this is how axion couplings are connected, are ALPs, if you want, whatever you want to call them. That's how the people calculate their properties. So all this chiral Lagrangian formalism is you can use in this other case. I mean, you apply it to this other case. Maybe one other thing. So in principle, okay, there can be couplings like d mu axion to these quark currents and so on. So you have to assume, in some models, people say the only coupling is this axion times this, and then you can go calculate. But if you had some more complicated theory, you could already have some derivative couplings here, and then you also have the GG dual coupling. And when you make the rotation, you shift the other couplings. But that shift, the S matrix doesn't care how much you put in here and how much you put in the mass matrix. Usually it's better to put it in the mass matrix because this GG dual term is like a total derivative. So without this field, it would be a total derivative. That's why the axion is derivatively coupled, because if the axion were a constant, this thing doesn't show up in perturbation theory. And the effects of theta are non-perturbative, basically. Okay, so then what's defined is this field u mu, which is I u dagger d mu minus I r mu. So that's the right-handed covariant derivative on u minus u d mu minus I L mu u dagger. And if I just forget about the gauge fields, this is u dagger d mu u minus u d mu u dagger, which if I then convert to x's is xi d mu xi dagger minus xi dagger d mu xi. So this is our old a mu field. And we had put an I over 2 here, so this is exactly what I was calling 2a mu. So it's called use of mu in the literature here. And then people define chi plus minus, which is u dagger chi u dagger plus or minus u chi dagger u. So if you remember when we were doing the baryon masses, we got m xi dagger, m xi dagger, etc. So that's why you get this chi plus or chi minus. And so these are like the building blocks. The u mu's are Hermitian, the chi's are Hermitian, etc. So if you look at the lowest order chiral Lagrangian in this notation, I wrote it over there in our old notation, it becomes L is f squared over 4, the trace of u mu, or with my angle bracket notation, plus chi plus. Because chi plus is m plus m dagger, that's the m plus m dagger. I mentioned that the tube absorbing the 2b into the m makes its coefficient f squared over 4. And I'll leave it as an exercise for you to show that the trace of little u mu u, it's in my notes, but let's not waste time on it, is the same as d mu big U dagger, which is the same as d mu sigma dagger. And I wrote it this way because we can now have background flavor fields. So this d mu here includes the background flavor fields. Okay. What else? So the thing we called V mu is now called gamma mu. And that's the positive combination of this. 1/2 u dagger d mu minus IR mu u plus u d mu minus IL mu u dagger. So it's basically what we've, I mean, the other formulation I mentioned was also done with background gauge fields and everything else. So I didn't discuss it, but it's basically just a one-to-one mapping of what was of the other notation. And this transforms like the gauge field, so this transforms like H gamma mu H dagger minus DH H dagger, exactly like V mu did. It's the same as V mu. And so you can define a chiral covariant derivative where the notation used is this nabla mu, which is d mu, plus gamma mu, we called it d mu, plus V mu, it's the same thing. Okay, so any question? I mean, this just makes it easier for you to go look at what the papers do. So we have three kinds of covariant derivatives. We have this kind of covariant derivative, which acts on fields transforming like H. We have a d mu, which is d mu minus IL mu, which is a covariant derivative for psi going to L psi. And we have d mu, which is d mu minus IR mu, which is a covariant derivative for psi going to R psi. So if you have a transformation law for any field and it has some L's and some R's and some H's, you construct the covariant derivative by using gamma mu's for the H parts, L mu for the L parts, and the R mu for the R parts. Okay, that's all. So you can now write down the covariant derivative of anything. And when you go to, okay, so first, any questions on this? They're not background condensate. So they represent, in fact, the electromagnetic field or the weak fields, because as far as the strong interaction dynamics is concerned, gluons don't couple to photons or W's and Z's. So you just think of the photons as some background field, and you're studying the strong dynamics in the presence of the background field. And so these really are the, you can do weak decays and electromagnetic interactions by using this. And as I said, for electromagnetism, you just, if you only had electromagnetism, you would substitute in this for L and R, and then you get the electromagnetic interactions of the pions. This is now okay, everything is an A. This thing is a photon. This is the photon electromagnetic field, not the axial A mu, which, yeah. So, okay. Now, when you go to higher order, you need derivatives of the u's and so on, because you can have two derivative operators and more. So what they've done is defined a thing h mu nu, which is by definition d mu u nu plus d nu u mu, a symmetric derivative. And the reason for that is that if you calculate d mu u nu minus d nu u mu, that is the antisymmetric combination, you can show, I didn't define this yet, but okay, you can show that this is f minus u nu. And okay, so sorry, we're just going to define a whole bunch of symbols. So f plus minus mu nu is u, f left mu nu, u dagger, plus or minus u dagger, f right mu nu. U. So linear combination of the right and left-handed field strength tensors over here. So the antisymmetric combination turns out to be redundant. The antisymmetric combination can be replaced, is equal to the field strength tensor, so you don't need to use it. You can just plug in the field strength tensor. But the symmetric one survives, so that's why the higher order terms are written in terms of h v nu, the symmetric part. And finally, the interesting thing about this chiral covariant derivative is you can write it, it looks like a gauge theory, but this gauge field is actually just determined in terms of the pions. And now you can calculate the field strength tensor of the gauge covariant, of the chiral covariant derivative, and that's defined to be gamma mu nu. And so these are your exercises to verify, just explicitly work out the derivatives, you know what V is, etc. And you can show that this thing is a quarter U mu commutator U nu minus I over 2 F plus mu nu. And just forget about the external field, but what you have is a sigma model, which is a curved space. It has a covariant derivative on it, which is like a geometric covariant derivative in terms of Christoffel symbols on the group manifold. And this curvature is the curvature of the group space. And the curvature tensor of the group space is, in fact, you can write explicitly. So this is a G mod H is some space, and this is the Riemann curvature tensor, basically. And the Riemann curvature tensor can be computed explicitly, and there's this interesting 1/4. So when we were writing these recent papers in geometrical methods for doing loop corrections, if you have a chiral perturbation theory, the Riemann curvature which enters into that is this piece. Yeah.
Will give you the electronic decay of pies.
So okay, so one way is to basically use a property. Well, let's just do it this way. So if you have an object like S bar gamma mu P left D, no, U bar gamma mu P left D, you can think of this as some spurion which transforms in a specific way under the flavor symmetry. This is an object which is it's in the whatever, the 1-3 matrix of an octet of currents, and the 2-3, it's this combination of currents. So you break it up, 8 cross 8 is 1 plus 8 plus whatever, 10, 10 bar 27, and this has an octet in it and a 27 in it. So you introduce what's a spurion, which transforms like, say, an octet or a 27, and then you have some operators like trace, S, and in my notation, there's some sigmas and sigma daggers, where let's say I had a 1, 2, 3, 3, and then you contract this with sigma, whatever, okay, 3, 3, 1, 2, something like this, and expand it out, and then you can get so there's an unknown coefficient, so you can't actually calculate the rate, but you can relate k to 2 pi to k to 3 pi, and so on, and then this allows you to calculate those rates. So if you look at Georgia's book on weak interactions, he discusses this, and there's some problems in the back of the chapter which tell you how to do this.
Some of the versions have seen like taking the quadratic part of L and then fitting it with L squared, fitting it with the data to get replacing it by pi.
Well, that's what they call vacuum saturation, and that's not true, basically. So you could try, you can see this is a product of two currents. So you could replace each of these by the chiral currents. It's just not true. I mean, it's garbage because the gluons in here interact with the gluons in here. And so this is a composite 4 fermion operator. It's not the product of 2 separate 2 fermion operators. So that's called a vacuum approximation or whatever. And maybe in the 60s when you didn't know what better to do, you could do that. But I mean, it's just wrong. So the delta I equals a half rule and so on is the statement that this thing fails by factors of 10 in certain cases. So the correct way to do it is just put an arbitrary number. Then you cannot calculate the rate, but you can relate different pions to each other. All right, so just a couple of more things. So one is, if you go to the p to the 4th Lagrangian, we have this operator L0 hat. I'll just give you one example, which was like a trace of d mu u dagger, d mu u, etc. So in this notation, it's the trace of u mu, u nu, u mu, u nu, etc. So things look a little bit different, but really there's just a one-to-one mapping of everything. And so when you go to order p to the 4th, you can have either 4 u mu's, because each u mu has a derivative, or you can have 2 u mu's and 1 chi, because the chi is the quark mass operator, and we saw that the power counting was that the quark mass counts as order p squared. Or you can have 2 chi's, and so on. So when you go to p to the 6, you can have either 6 u's or 4 u's and 1 chi, or 2 u's and 2 chi's, etc. And the last thing I'll mention is that here, when you put in this electromagnetic current, and let's work in the sigma basis, which we have been discussing. So sigma went like L sigma R dagger. The covariant derivative, including the electromagnetic field now, is d mu sigma minus I E A mu Q commutator sigma, because I'm making a transformation and Q is gauging the vector part where L is equal to R is the electromagnetic charge. So it turns into the commutator of Q. And so you can calculate diagrams like this. And okay, they're going to be infinite and need renormalization, etc. But what you find is that you will need a counter term or a term in the Lagrangian, which is the structure of Q commutator sigma Q commutator sigma dagger, the trace. So this is present because you can see that this is like a 2 of these vertices put together. If you were summing over all generators and so on, this would be an SU3 invariant object, but because I'm not summing over all generators, there's 1 photon. There are not 8 photons. And actually, even 8 photons would break the symmetry because I would only gauge the SU3 vector. If I gauge the entire SU3 left or SU3 right, you can show that this thing just collapses to a constant. But without that, you get some counter term here, or a correction, which with my naive dimensional analysis estimate would be E over 4 pi squared, because it's coming from 1 photon exchange. And then here you get some F squared lambda chi squared to make it dimension 4. And the homework problem is to do this trace. And you will find that the trace basically gives you pi plus pi minus plus k minus divided by F squared times some number. So this is Dashen's theorem that the electromagnetic correction to the charge pion and the charge kaon are equal. We just do the trace here and you find that the numbers are the same. And this gives you a correction delta m squared, which is alpha over 4 pi lambda chi squared. I mean, there's not an equal, I mean, there's some number here times some c, okay, where we expect c to be order 1. So this is where it's this diagram which leads to the electromagnetic splitting, electromagnetic contributions to the pion Hi, Rodrigo. To the pion masses. And if you plug in lambda is about a GeV and the alphas, you get that this side is about 800 MeV times C, and looking at the mass difference pi plus squared minus pi 0 squared, you find that this side is about 1,000 MeV. So again, we see that our counting, this naive dimensional analysis counting works reasonably well. You have a coefficient of order 1. But this is the term which gives you the mass splitting, the electromagnetic contribution to the pi plus and k plus masses. And then you can systematically go to higher order, put in more m's, more q's, whatever, and people have done that. No, so what this means is that if you just write down the most general EFT, you now have broken the symmetry. You have another object Q, which is symmetry breaking, just like M was symmetry breaking. And so
that's fine, but is lambda chi dependent?
Well, it has to be dimension 4, right? Because this is all dimensionless.
I understand that, but if I think from the, I'm doing Dimreg and I'm not supposed to get my cutoff.
Well, no, really what's happening is that your EFT has some diagram and QCD has some diagram and there's some matching calculation. We don't know how to do it. So that's really how you should think about it. So this is really this is in the EFT. So, I mean, as you can see, things start getting, when you do a real example, things start getting complicated because now you have the mass, you have the Q, etc. And then that's why some of these papers are 50 pages long and so on. But there's a whole literature. And as I said, people have worked to order p to the 6 for sure now. And I think recently the p to the 8 Lagrangian was worked out. It's a non-trivial exercise to count the independent operators. So maybe, there's Joydeep. Are you talking about it tomorrow? I mean, not tomorrow, next week. Yeah. So it's a hard problem, and even just classifying the operators. And then to actually do the 3-loop corrections is another something else. Okay, so I think I will stop here. I think you got some idea of what the subject is. No, the field strength. I mean, really think of L mu. So these are the background field strengths. So for example, if you just couple this to electromagnetism, you would really have an F mu nu, which is an electromagnetic field strength tensor, just the electromagnetic F mu nu. And you can have, I don't know, maybe I'll get 0 here, but you could have things like this. And that would be some coupling of pions to photons, which isn't just the covariant derivative. So just like, if you have of a muon, you could have a sigma mu nu, some anomalous magnetic coupling, which in QED is not there, but if you have some new physics, there's a magnetic moment coupling directly to F mu nu, which is not fixed by gauge invariance. There can be an arbitrary number here, and so there can be arbitrary numbers there. And this just allows you to include all of those pieces in the theory. So I think, where's the H mu? So this H mu nu, right, will have terms which are d mu pi. Because u mu has, so this is completely made up of pions. It's something like this. And I believe it comes in first in the p to the 6 Lagrangian, because in the p4th Lagrangian, everything is in terms of the u's, because of integration by parts and field redefinitions. But I think in p to the 6, you get terms like the trace of h mu nu, u alpha, things like this. So H mu nu is order p squared. So that's p squared, 2, 2, 1, 1. Yeah, so that's p to the 6. So you get things like this. Or H mu nu, I plus or something. So I don't know if in the notes, I might have put in the, anyway, there's papers by Bainans and friends, and if you look at order p to the 6, there's like, I forget, 117 operators or something. So it's rapidly getting to be a mess. And they actually calculate the running of all the 117 from the two loops, from the two loop L2 calculation. Yeah, the relation, yeah, so because of that Weinberg formula, right, the 2L plus whatever, yeah, so if you do one loop from L2, you get L4. If you do, sorry, yeah, 1 second. Two loops from L2 will give you L6. Well, the power counting is similar, but it's got that extra -1. So you still have the 2L from the pi. So every pion loop is moving you by 2. So there, one loop would get you. So we start with L1 because the leading Lagrangian is L1, and one loop would get you to L3, and two loops would get you to L5. Yeah, the same. I mean, because of this 2L plus the. Right. So you get the manifest counting from the 2s and the 1s and the 3s, and then you get the extra 2L. And the extra 2L is the same for baryons and mesons. So every loop adds 2 to the. Yeah. That's. I mean, so the baryon Lagrangian has its own set of parameters, and yeah. The key to doing good research is find a tree-level problem, which is interesting and nobody has done. Not the 3-loop calculation, I think. Yeah, so now, okay, so now you have, right. So now you have a power counting, and how do you do, okay, so again, there's endless debates here, but never mind. There's a quark mass, but there's mu and, let's say mu and md, and there's ms, and there's alpha. 1 by? Or if you, let's forget about even just this, right? And now you want to decide, how should I count alpha relative to u and d? Or how should I count ms relative to u and d? Because formally we're treating these the same, but s is 20 times bigger than that. So maybe you want second order in s to be comparable to this. Okay, whatever. So now you have to break things up more and decide what you want to do. And then people argue as to whether alpha should be treated as order p squared, or what do you want to do? But really, it's now a multi-parameter problem. Yeah. Yeah. Yeah, it's coming from the matching. Yeah, that's what you want to know, right? Yeah. That's right. So there's some the short distance physics is QCD here. Yeah, you cannot generate this thing in the numerator from a chiral loop in the EFT. Yeah, I'm leaving today. So if you have questions, lunchtime is like the last chance.
It's going to be served only at 12:30, so you have still 20 minutes.
Very good. So what I did not mention is the topological terms. So there's this whole story of the West-Zumino term. So West and Zumino actually worked out so you take some J mu LA, and that's proportional, well, some trace of TA F left mu nu, F dual mu nu left, 1 over 16 pi squared or something. That's the left-handed anomaly, and there's a corresponding right-handed anomaly. So in the case of photons, if you take a pi zero current, which is a T3, and here you would have a Q and a Q, and because the charges of the up and down quarks are not equal, you will get a non-zero trace. So that's the anomaly in the axial vector current, I mean the T3 axial current to gammas. And so West and Zumino actually worked out how to construct a term in the Chiral Lagrangian, which is not of this form. It's like some integral you have to do, which reproduces this. And not only that, it also has other contributions like 5-pion interactions and so on. And that would take like a whole lecture or more to just go through it. So they actually worked it out, and then Witten came up later with this more geometrical view of the same term. But yeah, so in everything I've done, there's in addition this topological term. And what the topological term is will now depend on the global structure of G mod H, and needs a more careful analysis because that C notation and so on is only sort of useful for a patch near the identity. So now you really need to know what the global structure is, and it's related to the cohomology classes of that manifold and so on. So that's also a very interesting subject, but. So this one thing I should say is this diagram with the pi zero, or the axial current, has a quark loop in it. And so it depends on the number of colors. So that was one of the tests, that the number of colors was 3 to get the pi zero to 2 gamma rate right. You had a question? Yeah. You should not include the eta prime in the Chiral Lagrangian. It's not there in some sense. It's the same as. Okay, so for baryons, which are 1 GeV, you have conserved baryon number. So the baryon goes along, and you can look at these soft pions bouncing off the baryon, and it interacts. Now, when you do the rho goes to pi. And now the 770 MeV going into the pions. You can't stop it decaying into 2 pions. And so you can't like do a rho going along and then do chiral perturbation theory like this, because there's also diagrams where it decays into 2 pions. And now this is not under any control of chiral perturbation theory. So the eta prime is like that. It's not a Goldstone boson. It's like 900 and something MeV. The expansion breaks down. In the large n limit, it would become a Goldstone boson, but then you have to decide whether the 1 over n expansion's under control when you're shifting it by so much, right here. I mean, Weinberg's limit was less than square root of 3m pi, which is whatever, 200 or 300 MeV. So the extra 600 MeV is coming from the 1 over n breaking, if you want. There's many things you would like to calculate which we don't know how to do. So that's life, I think. You have to find something which can be both calculated and measured.